Hi, Chris Guzmal here. We're now going to introduce the idea of an Herbrand logic. To justify it, we're going to talk a little bit about what a relation is in paying attention to a detail we might not have given enough attention before. The idea here is that relational logic does give us a large number of relational sentences, but the number of relational sentences is nevertheless finite. In an example here, if we have three object constants, two relations, and an arity of 1 and 2, then the Herbrand base is listed here. And it's substantial, especially for a human, but it's definitely finite. There's only 12 terms in the Herbrand base. Now, we do have quantifiers that allow us to shorten up sentences. So if we wanted to write P of A implies P of B, and P of B implies P of B, and P of C implies P of B, we could just say for all X, P of X implies P of B. But even so, both of these sentences are finite in extent. And that means that although it's more efficient to write things using quantifiers, there's not sort of this transcendent nature to it. And the reason is that relations are different than operators. If I were to write two conjunctions, I could then conjoin them. And so P and Q can be conjoined with R and S. But you can't have a relation of relations. You can't say likes red of X, comma blue of X. You might have thought you could do that, and you might have overlooked that detail in studying relational logic, but you can only give object constants to relations. So what if you could give something like a relation to a relation? Well, that would give us the difference between operators and relations. There's no limit to the length of a logical sentence you can build. It might be a little bit silly just to keep adding and a, and a, and a onto the logical sentence, but it's still unbounded. You can still make any logical sentence longer by adding another conjunction to it. But that's not true for relations. And that's why we're going to introduce functions formally in a minute. But right now, I'm just going to talk about the meaningful difference for a function. And that is functions can function on functions, just like conjunction operators can conjoin conjunctions. You can make a little song, almost like conjunction junction. What's your function? F of F of A and F of F of F of A, and that can go on unbounded. If we had functions in our Herbrand base, the base would be unbounded. The base would be infinite. And so there's this phrase, finitely axiomatized. If the Herbrand base is infinite, we can still specify the entire set as for all X, F of X. We have finitely described something about something that is nevertheless infinite in extent, because X can be F of A or F of F of A or F of F of F of A on and on forever. This means that now we actually in a position to understand this rather daunting sentence. In this lesson, we explore an alternative to relational logic called Herbrand logic, in which we can name infinitely many objects with a finite vocabulary. Okay? And we just showed how to do that. And the trick is to expand our language to include not just object constants, but also complex terms that can be built from object constants in infinitely many ways. And we showed how to do that by redefining the concept of a relation to be a function. And we construct terms in this way, we can get infinitely many names for objects. And because our vocabulary is still finite, we can finitely axiomatize some things in a way that would not be possible with infinitely many object constants. This is a little bit deeper. You're going to have to postpone fully understanding that last bit, but you know what we mean by finitely axiomatized. We've just covered that. So fasten your seatbelts as we head into Herbrand logic and discover that it's actually not that hard.